And what are the important things when you're developing a catalytic process? So this slide is meant to show the different things that are important during development. So we've got the reaction conditions, for example, whether they're solvent, temperature, pressure, concentration and reaction time. And the sorts of things as process chemists that we want to do, we might want to choose a specific range of solvents. So, for example, dichloromethane, very widely used in the laboratory, totally unsuitable as a plant solvent, first of all because of the volatility, but also toxicity aspects. And there are certain limitations on the ranges of solvents that we can use as process chemists. Temperature, you know, in a scale-up or in a plant, you know, you have ranges of temperature which are much more commonly used than others. If you use temperatures outside of the -20 to 150 range, you need specialised equipment or more investment, more capital, and therefore more cost in the process. Pressures, you know, typically a 1 to 5 bar pressure in standard plant. Of course, you can go higher pressure and you can go lower pressure, but that's again investment and cost within a process. The sorts of concentrations that we often aim for in a process are between 5 and 25% weight to volume. If we go more dilute than that, then it means that we're not productive enough in the process. And similarly, if we go more concentrate than that, we lose control, we have viscosity problems, we have, you know, many problems that occur due to the concentrate nature of the process. Reaction time. Typically, we'd look for reaction times between 1 to 18 hours. 18 hours is still quite long. And the reaction time or the cycle time is very important because that's the main component of the cost within a process. So the actual time that it takes to make the material is the time that you're operating the plant, you're paying the employees, using the services, and it's time that you're not making other material. So one of the jobs of the process development chemist is to try to get that cycle time as short as possible. So that has a much bigger impact on the productivity and a process than improving yield, for example, which, you know, is important because maybe it separates impurities, but cycle time is a really important part of that. The catalyst is an important component, of course, in the process, and we tend not to think about, at the lab scale, we don't think about availability of catalysts. But if we're scaling up, availability can become quite a big issue. And the cost of the process. So, again, a rule of thumb would be that we would look to have a contribution to the cost of making the product of around about £10 per kilogram. So if the catalyst is costing more than that per stage, then it's becoming the major cost component within the process. And therefore, you'd say, well, we need more performance from the catalyst, more turnover, to be able to get those costs down. And that's a difficult target to achieve. So it depends on the volume of production, of course, but that's sort of rule of thumb. Consistency. We don't tend to think about enantiomeric excess with consistency, but of course if you're making a product day in, day out, any variation in the enantiomeric excess has an effect downstream where you're purifying. So typically we'd be looking for variations of plus or minus 1% EE. Now in a lab you wouldn't normally monitor that difference, so it would be put down to analytical differentiation. But again, that can become important. And similarly, removal of the catalyst at the end. So if it involves metals or particularly precious metals, then removing those from, you know, tens of thousands of ppm down to about 10 ppm can be a very difficult thing to do. So consideration of how you remove the metal can become important. The change in the rate of the catalyst. This is something that during a process it's quite difficult to see what's happening to the catalyst. So if we do a typical batch reaction, then we observe either the product or the starting material, but what we don't tend to see is what's happening to the catalyst, and we assume that the catalyst is always doing the same thing through the reaction. But of course it's very often not. It's very often decomposing. And so we might get strange kinetic shapes in the reaction. We might even get, as I'm going to show you later, reactions that stop completely. So having some idea about the change in the catalyst performance, whether it's selectivity or some of that deactivation, can again be very important to having a process that's robust and reproducible. Again, one thing that is often not considered within chemistry are phases. So engineers always think about gases, liquids, solids, and how they meet and how they combine. And that has a dramatic effect on the choice of the reactor that you might use. So the way in which you mix these different phases, I'll show you in a minute, becomes very important. And similarly, energy as well, and the removal of, or addition of heating to a process can affect dramatically the way in which you scale up. And lastly, around process control. So again, in the laboratory, we don't tend to control things. In fact, I find it astonishing that most chemists don't even put a thermometer into a reaction and observe what the temperature is in the reaction, because that temperature is giving you a lot of information about the way in which those materials are reacting. In fact, it's a continuous measurement to be able to see, whether there's an exotherm in the reaction or not. So something as simple as that could be used. And we need to manage those exotherms, because if we don't, then we can end up having runaway reactions. Often the way in which we control a process is by having a limiting reagent. So if we put everything together as you would normally in a laboratory, the reaction rate runs at the kinetic rate, the rate of the reaction of the materials. But in a process, that's no good, because we're not controlling the energy balance in that. So the way in which we normally do it is by feeding one reagent in as a limiting reagent, and then that controls the rate of addition. We can control the exotherm, and if there is an exotherm, we can stop the addition, stop the reaction. We have control over that process. That's the way normally processes are run. But that has its own impacts on the process as well, as I'll show you in a minute. And sampling. So sampling from a large vessel can be very difficult, particularly if it's mixtures of gases, liquids, and solids in there. And so the use of in-line measurement or real-time measurement is becoming more and more important, but it's not an easy thing to do, as I'm sure you're aware. And lastly, something as simple as a reaction profile. Many chemists will look at the end point of the reaction, take a sample at the end point, or work the reaction up. But actually, there's loads of information that can be gained by monitoring a reaction with respect to time. So that reaction profile gives you not only kinetics, but it can also tell you about catalysts and so on. So those are some things and some sorts of rules of thumb around developing a process and scale.